So our next talk is from Peter. Peter finished his degree in software engineering at the Australian Nationality University and moved to Munich to work at the V8 team. On the V8 team, he is focused on performance of the ES6 features and on Node.js. A warm welcome to Peter.
Okay, hi again, everyone. Thanks very much for coming. So I'm Peter, and I'm going to be talking about high-performance JavaScript in V8. So like Johannes just said, yeah, my day job is working on V8 here at Google, and so far I've been focused on performance. So I've been working here about 9 months, and I've worked on the performance of new ES6 features in the language, and as well performance of Node.js and typed arrays and a few other things like that in JavaScript. So first of all, I just want to say that when we're talking about high performance in this talk and in the title, what I really mean is predictable performance of your JavaScript. So we don't necessarily care that much about how fast we can make one little benchmark run, but I'm talking about the overall performance of your application and how this affects users. So what they actually see when they load a page, how fast is that? So the structure of this talk is going to go a bit like this. We're going to talk a bit about JavaScript engine, so what V8 is, what the problem space is, why it's interesting, why I find it interesting to talk about. And then we're going to talk a bit about the past and the present of V8. So in the past, our optimizing compiler was called Crankshaft, and we're going to talk about that, some of the limitations it had, and some of the problems we ran into with that. And then I'm going to talk about Ignition and TurboFan, which is our new pipeline, which just went into stable this week. And I'm also going to talk about some interesting trends we see in JavaScript these days and how this relates to performance, because JavaScript has come a long way, even in the last 5 years. So first of all, you might say, well, why do we care about JavaScript performance? I have my machine, and it has 32 cores or whatever, and I have so much RAM, and it's so fast, we should just build faster machines and just not worry about it, really. Well, yeah, that's true for some people who have those machines, but what we see is that a lot of new users coming online, and particularly a lot of people using web apps where this interactive time is really important, are on low-end devices. So they're using $50 or $100 smartphones, they have slow data connections, and they really don't see things the same way that we do in terms of the speed. And we know that users click away from slow sites, and this translates directly into money. So if you have advertising or however your site earns money, you need to get people on your site, you need to get it loaded, and you need to actually engage them before they get bored or do something else. As well as that, we're not just talking about, say, a 3% performance gain here, or it loads 20 milliseconds faster or something like that. What we really care about is being able to enable new use cases with JavaScript. So 10 years ago, there wasn't really a whole JavaScript server stack where you could do everything like that. There were some projects working on that kind of thing, but nowadays we have Node.js because we're actually competing with other languages in terms of speed and performance on the server. What is a JavaScript engine anyway? What is V8? Well, when we talk about a regular program, we just talk about maybe some string input or something like that and some string output. And I want to convince you that a compiler is not really particularly different. So some people are like, oh, compilers, I don't know how that works, it's crazy. But this is basically what we're doing on a pretty basic level. It's just a regular program that takes some sort of string, and we call that string code. So the code you're running in your browser when you're writing ReactJS or something like that. And we're doing something to it according to the JavaScript spec. So for this really simple example, we're taking some string, which is some code, and we're doing some computation and returning some result. So you might hear people talk about these things like abstract syntax trees, parsers, interpreters, compilers, garbage collectors, all these sorts of things. And they are important for JavaScript engines, but really they're just abstractions we use to help us solve this problem. So what exactly is V8? So V8 is the JavaScript engine within Chrome, and that means whenever you're running JavaScript in Chrome, or you ship some JavaScript to your user and they run Chrome, it's running inside V8. So that's the compiler for JavaScript. And it's also the JavaScript compiler inside Node.js. So other browsers have their own JavaScript compilers, but they're all implementing the same specifications. So they all do largely the same thing, just in perhaps very different ways. Okay, so why is JavaScript so tricky? Why do we talk about the performance of JavaScript so much? JavaScript is really, really dynamic. And that's what makes it so difficult to make really, really fast, and why we've been trying for so many years and why we've made so much progress. So the typical case here is dynamic typing. So when we declare a variable in JavaScript, we're just saying, yeah, this is a var x, whatever. We don't say it's a string or an integer or something like that. And this information is actually really critical to the compiler so we can generate really fast code. And so we know exactly what we need to do. But in JavaScript, we don't have this information until we run the code. And this is great for prototyping and getting started and just running something together. You're not going to get all these type errors, and you can just see how it works. But in terms of making it really, really fast, this is the challenge for compilers. And JavaScript has this dynamic inheritance model too, so you can also change the prototype of something while you're running it, and this is going to change what methods are available on it and all this kind of thing. So all of these things just make it a little bit harder to really make a really fast code every single time. In the same way, you can dynamically evaluate code with eval, and you can monkey patch anything by using a getter or a setter, which is really useful if you want to write a library or a framework that's going to intercept things, like if you have a testing framework or something like that. But again, difficult to optimize. So the way compilers generally deal with this is we use something called speculative optimization, which basically means that we guess. So with this code here, you might look at it as a human, and it makes sense to you, perhaps. We see user.first and we see user.last, and we think, okay, these are probably strings that are names or something like that, and we're going to store them to this username property, and then maybe this is going to appear on the screen somewhere in Chrome. And when the compiler looks at this, it sees, okay, we have property loads of user.first and user.last. We have a plus operation, and then we have a store. Okay, that makes sense. But the compiler has all these questions that it can't answer statically. It can only answer them once we run the code. And the first question is, do these properties exist? So we don't know that every user object is going to have a first name on it. This could change between objects because we don't declare which properties objects have before we run the code. So do the properties exist? How do we access them in memory? So if this property does exist and we have, say, a pointer to this object, how far into this object is the value that we want? And lastly, what types are actually going to be returned here? So just because you have a user object and you call first on it once and it gives you a string, it doesn't mean from a JavaScript point of view that the next time you do that it also has to give you a string. It could give you a number instead. And then the plus operand has to deal with all of this complexity. So it has to say, okay, well, if I get two strings the first time, then I'm going to concatenate them, because that's what it does if you have a plus and two strings. If I get two numbers, then I also have to plus those together. And it has to be able to do this every single time it runs the code, and this can all change at any point. So the basic way a compiler deals with this is it runs initially some general purpose code that says, okay, we're going to handle every single case here. So we're going to load these properties and we're going to see what they are. And as we load them, we're going to gather some feedback on the types that we see. So we're going to say, okay, this was a string, that was a string, we're storing it to a string, and we're doing a string concat operation. And then what we're going to do, once we've run this maybe like 100 or 1,000 times or something, we're going to realize this is really hot code. The user really loves running this function. It's their favorite function. Great. We're going to generate some really, really fast code. We're going to make this user really happy. This function is going to be the fastest function ever. So we specialize this function and we say we're only going to handle strings. And maybe not only strings, but we're going to narrow it even further by saying we're only going to handle this type of string. And we're going to generate code that is really, really fast for this one case. And we're also going to put a check at the top of this code that says, okay, check everything is actually still a string. And if that's not the case, if, say, the 100,000th time we run this we don't get strings, then we're going to maybe bail out to a slow case and handle that differently. So we're going to say our speculation was wrong, or in other words, we guessed wrong. So if that happens, we're going to bail out and we're going to go back to some slower code. And then maybe later we can re-optimize it depending on what types we see. Here's a cute picture of a pig. I find it nice to have little breaks so you can just relax. So happy. Okay, so I want to talk about our Crankshaft compiler. And this was the optimizing compiler that we used to use in V8 for pretty much everything. So this has been around for quite a few years now. So the basic architecture of V8 looked like this. So we saw this box before which said V8, and we're going to look inside that box now. So we have our source code, and that comes into V8, and we put it into the parser. And the parser is just an algorithm which takes the string and turns it into an abstract syntax tree. And the abstract syntax tree is just an in-memory representation of the code. And we start to sort of see relationships between bits of the code in the AST. So in the string, we just have a flat string. But in the AST, we say, okay, we have this plus operation, and then we have two operands coming down off it. So you can start to get an idea of the structure of the code and what things actually mean. Then here we had two compilers. We had a baseline compiler, which is where we do this slow general case and we build up feedback. And then we had Crankshaft, which was the optimizing compiler. And this is where we would generate really, really fast code based on some assumptions we make. We would generate some assembly code there, and maybe we would call into some C++ runtime functions as well. And eventually we'd do some output, either by printing something to the console or moving something around, something like that. Crankshaft was starting to show its age, and there were some problems with it. So we couldn't support new language features, so all new ES6 features and stuff like that. That's not to say that Chrome couldn't support them or they didn't run in Chrome. They've been running there for quite a while, but we couldn't directly support them in optimized code. And this meant that we had a lot of potential for de-optimization. So if you would write your code in a way that Crankshaft could optimize really well, you would have a really, really fast piece of code and it would run great and everything would be happy. If something slightly changed, one of those really narrow assumptions was invalidated, then you would get on this really, really slow path, and we call this a performance cliff. There were some other architectural problems with it. You didn't really have a separation of the phases. We had a lot of handwritten code, so we're supporting 9 different architectures, so that means writing a lot of machine code for different architectures. And also the baseline compiler, full code gen, produced a lot of code. Every time you wanted to run one function, you would need to produce some code with full code gen before you could optimize it, and this kind of thing. So what did our communication process look like? Well, we had these really fast paths in Crankshaft, and people wanted to make their code fast, naturally. So people would go and hack on V8 and look at it, and they'd say, wow, if you do this, it will run a bit faster or a lot faster. And we're going to try and write all our code so that it goes exactly really fast in V8. This kind of worked for a while, but it's a bit of a brittle approach. So we would see a lot of performance advice floating around on Crankshaft, and if you go on Google and you search, how do I make my code fast on V8, this is what you'll find. And this isn't wrong. Well, it was wrong. No, it was right at the time, but it's not really right anymore. But this is what people would say, and it was generally of the format of don't use X language feature because it is slow. And unfortunately, this was kind of the case sometimes. So don't use let const, don't use try catch, don't use try finally, don't use for in, don't use generators, and don't ever use async functions. So this led to what we call Crankshaft script. And basically what that is JavaScript where you look at it and you go, why did they write that JavaScript like that? And then you realize that that JavaScript runs really fast in V8. This is not really a great way to write JavaScript, but it was kind of our fault. Okay, so here's some code, and basically what this code does is it just loops through a string, and it just wants to filter each character to check whether that character is valid or invalid, and there's a certain set of characters which are valid and which are invalid. So we have this giant literal array at the top, and that's actually too long to fit on the slide, but it has 256 literal values in it. And then we have some like manual loop unpeeling here, and then we're like indexing into this array for each character and checking it. So it sounds kind of fast, and it was, according to this comment. So they say that we did this because it's faster in V8 4.9 than using a regular expression. Okay, sure. I don't know, sure. That was the case. Is it still faster in V8 5, in V8 6 today? I don't know. So we sort of created these dependencies between the code you're writing and the actual compiler you're running on. And not only is the problem, oh, we're only targeting V8, when actually there are other JavaScript engines out there that people use. We're targeting the compiler within V8, and we're targeting a specific version of that compiler. So it's just way too brittle to work long term. And it becomes easily outdated. So is this still true? We don't know. It's much harder to read and maintain. So this is the function which does the same thing as on the last slide, by the way. So we just have a regex literal, and we go, okay, we're going to test this string against this regex literal. Cool, it's readable. You can actually see characters on the screen, so you have some idea what it's doing. This is really nice. So what would be great is if this ran faster than the thing on the last slide, because then people could just write code like this, and it would look great and be fast. So what we found was we weren't really supporting real-world use cases a lot of the time. Here's a second example of Crankshaft script that we found. This is a little bit of a cut-down example, but basically, if you use try-catch or try-finally anywhere in your code, then that function would never be optimized by Crankshaft. We just couldn't support the feature in Crankshaft because of some of the architecture of it, and so we would always bail out to slow code. And so if you were like, but I really want this to be optimized, you could just put the bit you want to be optimized in a different function, and then wrap your try-catch in another function, and then call into that function, and then the function you really care about is still going to be really fast, and your try-catch is somewhere else, and then you've solved all your problems, right? And it works. It's 1.27 times faster on V8 5.1. That's great. I mean, the code looks kind of funny, and if you did this everywhere in your code base, you'd have twice as many functions. But it kind of works. But actually, in V8 6.0 today, this makes literally no difference. You can do it either way. You can just inline this code straight into the try finally, and it doesn't really matter. Here's a picture of a dog in a banana costume. Love that dog. Okay, so Ignition and TurboFan is the new pipeline that we use now in V8. So what's different? Okay, it's largely the same, but from our AST we use a bytecode generator now, and we either go to Ignition or TurboFan. So Ignition is that base stage where we're collecting feedback and this kind of thing. But instead of a baseline compiler, we're now using an interpreter. And TurboFan, we have a different optimizing compiler now there as well. So what are some of the advantages of the new way we do it? Well, using an interpreter instead of a baseline compiler means that all the code is already there when we want to run this slow case. So we have some code we've pre-generated, and it handles all the different use cases. And then we just run through that, and we gather some type feedback. And doing it that way means that as opposed to using a baseline compiler, we don't need to actually generate code on demand. So on low-end devices that don't have much memory, we don't have all this stuff floating around, all these functions that we've only ever run once that we had to allocate. And also the garbage collector is a little bit happier because it doesn't have to like figure out how to throw out all this garbage we just created. So we have wider FastPaths that handle more common use cases. And we actually can support all language features with this new architecture. So you can use whatever language feature you like without having to worry about manually splitting it apart and making this like Franken code. So it's much more predictable and stable, at least from what we've found from measuring. So these are some of the real-world performance results of Ignition and TurboFan. And these measurements are basically the startup time of websites. And this is measuring the actual website using your browser. So it's not a synthetic test or something. We just like measure start to finish. And we see a much bigger improvement on mobile than we do on desktop. And this is kind of what we expected from the interpreter. It really benefits mobile and when you have low memory and that kind of thing. But it also helps a lot on desktop, except for Reddit. I don't know. We had to save space somewhere. Yeah. Okay, so fast JavaScript for TurboFan. What would that look like? Because I just showed you all what Crankshaft script looked like, so now you're all like, tell me how TurboScript works so I can make it really fast. We don't really know yet. What we hope is that TurboFan script just looks like regular JavaScript code that you'd actually want to write. This is kind of the ideal world, right? Like, you have really nice code and it looks nice and you can understand what it does and it's fast. That would be awesome. And as well as that, your code should work fast on any engine. So if your code is like 200 times faster on some other browser, then this is a bit of a flag that something weird is going on. And yeah, we just shipped Ignition and TurboFan to stable this week. So if you have Chrome stable or if you've heard of that, then this is cool. This is running now in your browser. So what are we seeing in JavaScript and how does this relate to everything I just talked about? So we see a lot of people using transpilers and frameworks and everything like this, and there's really a lot more to the JavaScript development process than just like sitting down with an editor, writing a bit of JavaScript and like shipping it to your user. So there's a few trade-offs between using transpilers, and I just want to sort of cover that trade-off space. It's actually quite complicated to think, do I want to use this? Yeah, how do you decide that? Well, it used to be that it was actually a lot faster because ES6 features were only just implemented in Chrome and other browsers as well, and they were a lot slower than whatever you could do in ES5 that did the same thing. So I'll give an example of that. But as we're optimizing for these new features and plugging them into our new pipeline, they're getting a lot faster. So these returns are sort of diminishing in terms of how much faster you'll get by transpiling that thing. Another really big thing is that we're realizing that we're actually losing some performance by transpiling our code before we send it to the user, because transpiled code is often a lot bigger than regular code, right? Like usually a factor 10 or 20 or something like that, depending exactly how it's transpiled. And we have to parse all that code. We'll see some stats on that later, but basically we have to look at all that code and we have to get it into the abstract syntax tree so we can see what it does and whether we need to run it. There's some compatibility issues you might want to think about as well. So transpiled code not always equivalent to original code. So you might be using some transpilation for ES6 to ES5 feature, and then you're like, okay, I'm going to turn off the transpiler, and then your code does something different. It's totally possible. So the transpilers aren't always spec compliant, but the engines sort of have to be. But sanity is an important consideration too. So it's nice to develop with these nice modular abstractions where maybe you just write a little bit of code here and there, and you have a nice module system, and then you have some system which transpiles it, and then you have some system which like packs it all together into one file, and then you have like a minifier, and then you ship that to your user, right? And you can't read this code you ship to your user, but it's fast, we know that. So this is interesting, but maybe it's a bit harder to debug that code because you didn't write it. And yeah, like I said, sometimes there's parsing cost issues there as well. So what about ES6 features? So this is like the most basic example of an ES6 feature, and this is one that I worked on. So in ES6, you can do a spread call, which is where if you call a function that takes a variable number of arguments, you can pass like an array or something that's iterable, and you just put this ... in front of it, and then this like spreads. I don't know how to explain it. It spreads the arguments and calls it with a variable number of arguments, right? So this is a lot like the apply function prototype apply in ES5, where you can call it just with an array, and it'll basically do the same thing for you. So it used to be that if you transpiled this, it would go to the second version, to the ES5 version, and it was like so much faster than the ES6 version. So everyone just thought, why would we ever use the ES6 version? So we decided to prove them wrong by making the ES6 version 19 times faster. Now you want to use it. I mean 19 times faster than it was before. So basically they're about on par now. So the performance reason is not really a reason to not use that anymore, if that was something you were going to use anyway. So in terms of shipping codes to websites, the amount of JavaScript we're shipping to the actual end user has just been increasing ever since JavaScript was invented. So we're shipping something like 420 kilobytes of code to the average website, which is a lot, especially if you wrote that code by hand. Yeah, as I said, this actually increases the parsing time, and it surprises a lot of people that V8 actually spends like 15 to 20% of its time in parsing when you're starting up a website. So if you can reduce the amount of code you're shipping, that's awesome. It's going to be really fast. So some takeaways from this talk are, please don't write any more Crankshaft script. I don't want to see it. ES6 features are pretty much ready to go in V8. Like, yeah, we'd love to have people test them out. And if you run into any weird performance things or something like that, what we're trying to do is just optimize for the general use cases that people have. Particularly if you're writing frameworks or libraries or something like that, we're going to get a lot of traffic from your code. So we want to hear about how you're using new features. We want to have you test out the new pipeline. And you can log a bug on Chromium, or you can send me an email, and I'll log a bug on Chromium. And yeah, we're just interested in use cases, particularly if it's like way faster on one browser or something like that, or it's like suddenly gets really slower. That would be really good to know. So thanks for listening. All right, questions?
So we shouldn't write any more Crankshaft script. And you say there shouldn't be any more performance talks on how to write good JavaScript for, what's it called?
TurboFan, yeah.
Yet last month I saw a talk by Franziska Hinkelmann of your team saying how to write fast JavaScript by, for example, not changing types of variables,
yep.
keeping the property names the same, and things like that.
Yep.
Yeah,
you got to formulate it as a question.
Isn't your recommendation rather to use something like TypeScript or something typed, which is always going to be a bit faster than if you don't use it, if you just write out JavaScript?
Yeah, so there's a few things there. So the pieces of advice that were floating around a few years ago, there were basically two categories. There was the do not use X feature category. Okay, that's the category which is now wrong. So there was other advice floating around as well, which was try and keep your code static-ish, if you can. So if you're using an object, which like you're going to add some properties to it later, then V8 is going to change its underlying representation of that object, and then we might have done a speculation on the first representation. So if you can initialize all the fields you're going to use, like in the constructor of that object or something, like set them to null, so there's actually something there, then this hidden class will always be the same. So I think that's what Francisco's talk was talking about. So that sort of advice about keeping things vaguely static is still good advice. And that's also good advice for other engines as well. So what I like about that advice is it's not V8 specific. So pretty much all JavaScript engines are doing something like this, in terms of they take this like chaotic world of things that are always changing, and they say, okay, well, if we just pretend that everything doesn't change all the time, then we can have a happy world where things are fast. And so generally, if you can help that along by making your objects more static-like, then that helps. There was a second part to your question. That was it. Okay, I've answered your question. Great. Yeah. Yeah.
I have a question. Right now, the only thing that's stopping us from using ES6 features completely without better dependencies on the server in Node is the import statements. Can you tell anything about the future regarding that?
Yeah, so you're talking about use of modules and stuff like that. Yeah, so I think modules are being worked on right now. Yeah, I don't know the exact status of it, but yeah, that is coming.
So
okay.
at some point you don't have to require anymore, but you use the same syntax that you use in the browser.
Yeah, I believe so. My understanding is that modules aren't quite at the end stage of the specification yet, so there's still a bit of like work to do, is to figure out exactly what that syntax is going to be and how it interacts with the other module systems. But yeah, that is the next big thing. That's what we hear.
An alpha of Chrome already has.
Yeah, but Node doesn't support it. Node.
Yeah, so unfortunately with Node, so it's good in some ways because we're updating I mean, everyone who uses Node, a particular version of Node, is using the same version of V8. And you know when you deploy a version of Node, it has this version of V8, which means you know exactly what features it supports. So in some ways, Node is the first people who are using new ES6 features. Yeah.
Does your AST contain any types? If you can, sure, you have types. A TypeScript compiler has this way. If you have your instance checks, then it proves that you're using the correct type.
Oh yeah, that was the second part of your question I forgot about. So TypeScript and stuff like that. So okay, so if you put a string literal in your program, then yeah, we know that's a string literal. So like say you wanted to add two string literals together. I'm trying to think if there's any way you can monkey patch that. I can't remember. Probably it's JavaScript. But yeah, so we do take advantage of some simple operations like that, but in general, it's way too dynamic. So there's crazy things you can do that you can't rely on. So you can say, yeah, we know this thing's a number. Okay, but numbers have a prototype. Okay, has the user changed the number prototype? We can't tell in this function. So there's all these ways you can like hack in and monkey patch things that are just so dynamic that we generally don't know about it. But as much as possible, that makes sense. Yeah.
There's something to freeze the objects, like make them static, you can change them anymore?
In terms of the underlying map, like data structure we use in V8 that tracks this object, no. Because this is just something V8 does as a performance optimization, and it's not something the language specifies. So in general, it helps if you have a class for your object and you use a constructor and you initialize all the fields you want to use in that class, even if you don't have data for them yet, but just set them to null or something so they're actually, and that will initialize this underlying map that we have, and it'll say, okay, we have this type of property here. Or if it's a string, make it an empty string, and then the type won't change, that kind of thing. So if you do that in V8, you can actually run it with flags like trace map transitions or something. I'm not exactly sure what the flag is, but you can get this information out of V8 as well if this is like a hot section of your code that you really care about. That's not to say you have to do this kind of thing for every function or every object you're using, but if it's like the hottest object in your code and you like slam it in some really hot loop, then you might want to think about this kind of thing. Yeah.
How much cost is like versus the fallback?
It's generally like hundreds of times faster. Yeah, that's generally.
So if you have like these standards, like additional something, like you add two numbers, how many checks does statement go before it's really executed?
Yeah, so in the interpreter, adding is going to be probably particularly slow because when we add, we're using, what we're really doing is we're using the plus operator. And unless these are literally two number literals, then we don't even know these are numbers. So that's going to be really slow because we're going to have to go into some runtime function, which is going to go, okay, what are the types of these things? And we're going to do that every single time. We're going to perform all these redundant checks every single time. You could actually test this with V8 if you take the command line version of it and you want to just run some code. You can put no opt or no turbo or something like that. You can have a look at the flags, and you could just say run something for a really long time just in the interpreter, and then you can run it with always opt and then run it with the optimized code, and you could check for something like that how much faster it is. But generally, it's like somewhere between 10 and 100 times.
Maybe better not concatenate strings, for instance, the plus sign, or is it then better to use like a literal?
Well, I mean, it's fine. Sometimes you can't help it. Like when we're writing little benchmarks and stuff like that, I mean, if you have like one string literal and another one and you plus them together, then this is not really realistically what you do when you write actual JavaScript. Like you're pulling your string out of a database or from some API, and then you have to plus it to something because you just need to change the string. And in that case, it's not a literal. It's something you got from somewhere else. But TurboFan actually handles these cases really well. I mean, if you have a function and it takes two strings and concatenates them and does something else and stores them somewhere, if they're always strings, then TurboFan will realize that, and it will go, okay, they're this type of string. I know that I can just check the length, and then I'm going to allocate the whole buffer, and then I'm going to copy the contents in like this, and then we can do this really fast. So you don't have to avoid those kind of things. TurboFan is good at optimizing those kind of things, but only if they're always strings.
Last question.
Yeah.
So you have an object and it has a property, and it should be a string. You just mentioned before, just enter an empty string or something. Would it be faster to have an empty string instead of now? Like, is it visualized?
We are going to hack.
Yeah, I mean, it depends what you do. If you pass that object into an optimized function 10,000 times, and we gather all this feedback, an unoptimized function, we gather all this feedback, this property is always null and you're always accessing it, and then we speculate on this type always being null, and then you change the property to a string, this is going to throw our optimizing compiler out a bit. But also, this is quite a strange pattern to use an object for ages and then suddenly completely change that object. Like, it doesn't really make a lot of sense to me. So yeah, I don't know. But you can test these things, yeah. Okay.
Thank you very much.
Thank you very much.